Hi, I'm Kierston Sanford, and I'm sitting here with Dr. Michio Kaku. Thank you for joining me today.
Glad to be here, Kierston.
It's wonderful to have a physicist and a science educator such as yourself here to be able to speak with me. You are on a book tour right now. You've written a book, The Physics of the Impossible, which is really exciting and very interesting. What was it that kind of drew you? I mean, you write physics texts and you write popular books about physics.
Well, when I was a child, I had two childhood heroes. The first was Albert Einstein. When he died, everyone was talking about the death of the greatest scientist of the age. But everyone said that he didn't finish his masterpiece, the unified field theory, the theory of everything. I was a child. I was fascinated by this story. And I said to myself, I want to be part of that quest to finish what the greatest scientists of our age could not finish, the theory of everything. But I had a second hero, too. I used to watch Flash Gordon on TV. I was like glued to the TV set. But you know, after a while, you learn the facts of life. I didn't have blonde hair. I didn't have muscles.
Right.
And I said to myself, now wait a minute. It's the scientist that makes the series work. It's Dr. Zarkov. He invents the starship. He invents the ray guns. He invents the city in the sky, right?
Right.
Without Dr. Zarkov, there's no Flash Gordon. Without science, there's no science fiction.
Right.
So I said to myself, when I become a physicist, and I know exactly the boundary between the edge of physics and science fiction, that I'm going to write a book for somebody like me as a kid, wondering about invisibility and teleportation, starships and time travel. Well, now I'm a physicist, so I can write a book like this. And they told me, well, it's impossible that a book like that with physics in the title could hit the New York Times bestseller list.
And now?
And it happened. The impossible happened. It's number 12 on the New York Times bestseller list. So there are a lot of people out there just like me watching Star Wars and Star Trek and Terminator and then wondering, is it possible? Well, this book is for them.
Absolutely. And the question also, you say there's no science fiction without science, but that goes in the reverse also. Science fiction also drives science questions.
That's right. Take a look at Edwin Hubble. He's the greatest astronomer of the 20th century, discovered the expanding universe. But originally he was a lawyer. He was going to be a country lawyer, and that's it. But as a child, he read Jules Verne. And he had a romance of the stars. And he quit being a lawyer, went to graduate school at the University of Chicago, and he was in a rush, a real rush, because he was, much older. And he said, I'm going to make some big breakthroughs, and he made the biggest breakthrough of the 20th century, the expanding universe, which gives us the Big Bang.
Right, and it's led to so many other ideas about how the universe works, the concept of dark matter, dark energy, people looking at how far back time goes and what started everything out.
Gee, this is all the things I do for a living.
Yeah, I know.
That's my day job.
That sounds rough. What are some of the, for you, the most fascinating topics in this book?
Well, we used to consider invisibility impossible. I teach optics, and I would tell my students that invisibility violates all the laws of optics. Every optics textbook in the world says the same thing. And 2 years ago, I was proven wrong. Every textbook is wrong. Think of a boulder in a river. We know that water can wrap around a boulder and reform. So if you're downstream of a boulder, you have no inkling that there's a boulder upstream.
Right.
But light cannot do that. Or so we thought. We said the light cannot wrap around an object, so invisibility is impossible. 2 years ago at Duke University, they did it.
Right.
They did the impossible. They got an object like this, shown microwave radiation around it, and proved that microwave radiation wrapped around this object as if it was not there at all. And a few months ago at Caltech and in Germany, they showed that at a microscopic level, red light and green light can also bend in a way that was considered impossible. Which means that within 10 years, we will make an object disappear under, let's say, red light. After that, the three primary colors. And after that, Harry Potter, watch out.
With his cloak of invisibility.
Yeah, that could be coming very soon.
So I'm going to get a little more conceptual with that idea. objects themselves, we use the bending of light to be able to gauge distance between ourselves and far-off galaxies, between ourselves and other stars, to be able to determine, you see light in the night sky, and we use the bending of light, the red shift of light as it passes around objects and is bent by the gravitational field of those objects. Are these objects that a cloak of invisibility would cover? Do they not have a large enough gravitational field that it would affect the bending of the light as it passes, or is it?
These are called Einstein lenses.
Okay.
If you have a galaxy, light will actually go around the galaxy and be distorted, giving you a ring pattern, which we can actually measure.
Right.
And that's how, with the Hubble Space Telescope, we can actually detect the presence of dark matter. Dark matter is invisible. If I had it in my hand, it would be totally invisible. But we see it because light bends when it goes through dark matter. Now, ordinary matter, you can't do that. Ordinary matter will not bend light in that way.
Okay.
How does it work? A metamaterial has tiny impurities in it. And these metamaterials we thought were impossible to construct. But now we're making them every day.
Yeah.
Tiny little impurities. As light or microwaves goes through the material, it kicks. It kicks the microwave beam in a way once thought to be impossible. And that's why it can wrap around objects. So, guess who's funding this research? The Pentagon.
I'm guessing Department of...
They're not stupid. They spent millions building stealth bombers and stealth fighters, which are not really invisible.
Right.
Under radar, they appear as like a large bird. Now we're talking real invisibility. Now, to be fair, there are countermeasures you can also have.
Such as?
If I have the Invisible Man, I can throw sand in the air, and the sand will then trace out the outline of the Invisible Man. Or I can put a bed sheet and then trace out the outlines of the Invisible Man. So the Pentagon has to realize that, yes, they're spending a lot of money on invisibility, but there are countermeasures you can take against the Invisible Man.
So we've got invisibility. I think one of the big ones, the big questions, time travel. Are we ever going to be able to jump past the problems of space-time to be able to move back and, go back to the age of the dinosaurs or go forward?
Well, my colleague Stephen Hawking was famous for saying that time travel is not possible.
Right.
Because, well, where are the tourists from the future? They're not taking my picture, so time travel is impossible.
Maybe they are.
But maybe they're invisible. Invisibility is not
Putting
out
it
of the
all
question.
together.
Plus, maybe we're not interesting to them. If you go down a country road and see an anthill, do you go down to the ants and say, I bring you trinkets, I bring you beads, I give you nuclear energy?
No, you sit there with a magnifying glass and
burn a few, or step on a few of them, right? So what makes us think that we are so cool that an intelligent species in outer space or our descendants are going to come and visit us?
Yeah.
However, if somebody knocks on your door one day and claims to be your great-great-great-great-great-granddaughter, don't slam the door. Because it's possible that centuries from now, our descendants will be able to manipulate the power of a black hole, a star, go backwards in time, and meet their illustrious ancestor that they've all read about in the history books.
Which would be so great. One aspect of time travel that has come up for myself and some friends talking in conversation is if space and time are so inextricably linked. And we are on a planet that moves in space and through time. So if we were to say, I want to come back to this place, but, 100 years in the past or whatever it happens to be, would we actually be able to get back to the exact place that we want to, or would we end up in deep space?
Well, time is like a river. Well, first of all, Newton thought that time was like an arrow. You fire the arrow, it never deviates, always goes in one direction, and 1 second on the Earth is 1 second on Mars, is 1 second on Jupiter. That's the Newtonian universe. Along comes Einstein, who says, not so fast, not so fast. Time is like a river, old man river, that speeds up and slows down around stars. And we measure that every day. The GPS systems. Time is actually slower up there in outer space than on the Earth. And the Pentagon cannot fight wars without the GPS system guiding its cruise missiles. Pentagon generals have to be briefed on Einstein's theory of relativity in order to fight a war. Okay? Now, the new wrinkle on all this that's causing all the excitement is that the river of time may have whirlpools. And the river of time may fork into two separate rivers.
Okay.
And this explains the paradoxes of time travel. For example, what happens if you go backwards in time, meet your teenage mother as a teenage girl, and she falls in love with you and spurns your father? How could you be born if all of a sudden your parents never met because you got in the way?
It's Back to the Future.
Right. Well, we physicists think we can explain that paradox. We think that the river of time may fork into two rivers, so that when you go backwards in time and meet Abraham Lincoln at the Ford Theater, and you prevent him from being assassinated, you've prevented somebody else's Abraham Lincoln from being assassinated. Your past is fixed.
Okay.
Your timeline cannot be changed. You've gone backwards in time to meet somebody else's timeline, and you've now created a parallel universe in which Abraham Lincoln was not assassinated at the Ford Theater.
So, Back to the Future could happen, but the Terminator would not necessarily be so possible.
Well, the Terminator goes possibly to a parallel universe where he can, in fact, kill the mother of the future leader of humans.
Yeah.
But in his universe, he cannot. He cannot kill his the mother of the leader of the humans in his world, or else history would be impossible. If you go back and meet the dinosaurs and you accidentally step on a rodent who happens to be your great-great-great-great-great-grandmother a few million times removed, how can you live if you just kill the ancestor of all humans? So we think that it is possible to resolve all time travel paradoxes. Then the question is, well, why don't we build one and set the dial and see whether it works?
Yeah.
There's a catch.
There's
always a catch.
Yeah.
The catch is you have to be what we call a type 3 civilization, capable of manipulating the power of a black hole, the power of a star. Space and time is a fabric. We can bend the fabric of space-time. We measure this in a laboratory. We measure this around stars. But to rip the fabric of space-time, that would require the energy of something like a black hole.
So our technology and our scientific abilities need to advance tenfold, 100-fold.
That's right. But we're getting there. A lot of the things you see on Star Trek we think will in fact be possible. For example, the teleporter, right?
Right.
Everyone says, wow, Captain Kirk just zapped between A and B, right?
Yeah, I don't need a flying car if I've got a teleporter.
Who needs to have an airplane if you can just push a button, right? Well, first of all, Roddenberry invented the transporter because Paramount Studios says it costs too much money to have rockets land and take off each time. So teleporters were invented by Roddenberry as a measure to cut the budget of the Star Trek series.
Oh, I love it.
Now, we physicists today can teleport particles of light called photons. The world's record is 100 miles.
Wow.
From one Canary Island, we can zap a photon and it materializes on another Canary Island. We're going to do that next for the space shuttle. We're asking NASA for permission to set up in the space shuttle a device where we can teleport photons into space and back. And after 2020, when we go to the moon, we're going to teleport to the moon. There's no limit to how far we can teleport.
Wow.
And within 10 years, we'll teleport the first molecule, like water, for example. We can teleport beryllium. We can teleport atoms of cesium. Next will be a molecule, like water. After that, DNA. We may be able to teleport a virus. We may be able to teleport life forms. Now, Captain Kirk is more of a problem. Captain Kirk consists of 50 trillion cells. That's how many cells we have in the body. That will require centuries of work. But hey, Star Trek takes place in the 23rd century. That gives us enough time.
That's about right.
About then, we may be able to eliminate train tickets, eliminate plane tickets, and solve the energy crisis by pushing a button.
That would be so amazing. Now, is it actually, is it in teleportation now? Is it the photon that is in one location that you are taking that exact photon and transporting it to another location, or is it an exact copy or replica?
Well, if you're a true Trekkie, you know that the original is destroyed
Yes.
and a carbon copy is created at the other end. We destroy the information content of the original cesium atom or beryllium atom. We then create a copy of it elsewhere, and then you begin to wonder, if you teleport Captain Kirk and his atoms are destroyed, you saw him dying, who is this pretender over here who has the same memories, the same information content, the same genome of Captain Kirk over there? Where is the soul if you can destroy somebody and literally resurrect them someplace else? We think about this problem because this is an engineering problem now. It's no longer a question of physics. It's an engineering problem, a very big engineering problem. But you begin to wonder what happens when you teleport life. You know, what is being teleported? The essence of life, the soul? You know, you begin to think about these cosmic questions. Even physicists think about these things.
Yeah, well, I think it's those big questions. Theoretical physicists seem to come up against those throughout their entire careers.
That's why I became a theoretical physicist. I wanted to bump up against those big questions.
Constantly. And so that's another question I was really interested in, is that I've heard that the majority of theoretical physicists are incredibly spiritual and have a great appreciation for the concept of consciousness and the soul and the universe and where it came from, because these are the questions that they're constantly asking. For yourself, what's your view on life, and where is it? What are we doing when we teleport life, if we ever get to that point?
Well, if I knew the answer to life, I would have an inside track up there.
Right. As would anybody, yeah.
But let me tell you how we physicists view things, right? For example, Einstein was asked the big question, is there a God? Is there a meaning to everything, right?
Right.
And here's how Einstein answered the question. He said, there really are two kinds of gods. We have to be very scientific. We have to define what you mean by God. If God is the God of intervention, the personal God, the God of prayer, the God that parts the waters, then he had a hard time believing in that. Would God listen to all our prayers for a bicycle for Christmas and smite the Philistines for me, please?
Right.
He didn't think so. However, he believed in the God of order, harmony, beauty, simplicity, and elegance, the God of Spinoza. That's the God that he believed in, because he thought the universe was so gorgeous. It didn't have to be that way. It could have been chaotic. It could have been ugly, messy. But here we have the fact that all the equations of physics can be placed on a simple sheet of paper.
Right.
Einstein's equation is only 1 inch long. And the quantum theory is about a yard long, but you can squeeze it onto a sheet of paper.
Right, with a small enough font.
Right. And with string theory, you could even put those two equations together. And string theory can be squeezed into an equation 1 inch long. And that equation, by the way, is my equation. That's string field theory. That's my contribution.
Right.
But we want to know, well, where did that equation come from? You know, this is what Einstein asked. Did God have a choice? Was there any choice in building a universe? When he woke up in the morning, he would say, I'm going to create a universe. I'm going to be God today. What kind of universe would I create? This is how he created much of his theories.
With your equation of string field theory and your study into the topic, do you find yourself agreeing with that concept of these multiple universes with many different incarnations, and maybe ours is one of many different types of universes?
You mean to ask me, is Elvis Presley alive in a parallel universe?
Yes.
The answer is maybe, possibly so. Let me explain. We physicists believe that our universe is like a soap bubble. We live on the skin of the soap bubble. We're like flies trapped on flypaper. We can't get off our soap bubble. But it's expanding. In fact, it's actually accelerating. We can actually see the end. We're all going to die in a big freeze when this gigantic bubble gets bigger and bigger and bigger.
And we lose enough energy that it's very cold.
Yeah, and as
things stop moving.
Right. And as that great philosopher of the Western world once said, Woody Allen, he once said, quote, eternity is an awful long time, especially toward the end. Well, we physicists now believe there are other soap bubbles out there. There's no longer a universe. There's no longer a one world. There are many worlds. There are other soap bubbles out there. And these soap bubbles are called membranes, or brains for short. And they can collide. They can peel off, bud other universes. And we're going to test this theory in the coming years.
Yes.
Okay. All science is reproducible and testable. That separates us from religion, which is not reproducible and not testable. In 2014, NASA will launch a satellite, LISA, L for laser, which will detect vibrations from the Big Bang itself. Now, we have taken baby pictures of the Big Bang. Some people don't believe in the Big Bang theory, but that's okay. It's a free country. We have photographs of it. We can photograph the electromagnetic shock wave, the explosion. They're gorgeous photographs. They're on nasa.gov, on the website of NASA. But that picture of the Big Bang is from 300,000 years after creation, when atoms begin to condense. We want to get it at the instant of creation itself. And we want to actually photograph the universe coming out of the womb.
Wow.
And maybe there's an umbilical cord connecting us to a parent brain, another universe. We don't know. But this is really deep stuff.
Yeah.
We're going to go before the Big Bang with the next generation of space satellites. You see,
I think you just completely blew my mind. It's gone.
And we're also going to test these theories on the Earth as well.
Yeah.
In May, the Large Hadron Collider gets turned on.
I'm so excited about that.
It's the biggest atom smasher on the planet Earth. In fact, when I was in high school, I built my atom smasher. When I was in high school, this is much bigger than the one I built when I was in high school.
I'm hoping yours was smaller.
Mine only weighed about 500 pounds. This one is 17 miles in circumference. You could put the city of Geneva inside the machine, in fact. And we hope to create mini black holes, sparticles. These are predictions of string theory. Now, mini black holes are not dangerous, so don't think that Geneva is going to be swallowed up by a black hole.
And then shortly thereafter, the entire planet and then the solar system.
That's right. It's not going to happen.
Right.
These are microscopic subatomic black holes, and the energy of these black holes would barely light a light bulb. So you don't have to worry that we're going to be sucked into the string theory by creating mini black holes.
Right.
But we hope to create sparticles, superparticles, which we think make up dark matter. We think that most of the universe consists of a higher musical note of a vibrating string. So we do think, though we can't prove, that everything we see around you consists of tiny rubber bands that are vibrating. But these rubber bands can vibrate at higher frequencies. We think that the next set of frequencies is sparticles and dark matter. And we hope to test it at the Large Hadron Collider.
So as of May, we have the beginnings of the actual investigation into the predictions made by string theory.
Right. And then people ask the question, well, how come the Americans aren't doing this? How come the Americans have to knock on the door of the European Union? Because our machine was canceled in 1993.
It got under construct. They started constructing it and
Congress gave us $1 billion to dig
yeah.
a hole. And they canceled the machine, gave us a second $1 billion to fill up the hole. $2 billion to dig up a hole and fill it
back up.
Right.
Right.
So why was it canceled? And why do I do this? Why
Politics.
do I speak before people? On the last day of hearings, one congressman asked a physicist, quote, "Will we find God with your machine? If so, I will vote for it."
Oh my
The
goodness.
poor physicist didn't know what to say. So he said, we're going to find another subatomic particle. Well, you could hear all the jaws hit the floor.
Everyone, that's it?
And they said,
Yeah.
$11 billion for another god-darn subatomic particle.
Right.
They canceled it the next day. So we physicists, in our minds, over and over and over again, have played that scene.
Yeah.
How should we have answered that question? How should we have justified an $11 billion atom smasher that is now being built in Europe?
Yeah.
I would have said something different. I would have said, God, by whatever signs or symbols you ascribe to the deity, this machine, the super collider, will take us as close as humanly possible to his or her greatest creation, Genesis. This is a Genesis machine.
Wow.
We're going to recreate Genesis chapter 1, verse 1 with this machine. But we didn't know how to answer it, so they canceled the machine. And
Hindsight is always great, isn't it?
And now we physicists are knocking on the door of the European Union asking permission to get on their atom smasher.
But there are many European There are many European scientists who are also doing the same, asking the same questions, and so hopefully they're going to get into it.
Right. It's just that the focus is leaving the United States and it's going to Europe. So that's why I do this. Yeah, some people ask me a question. You're a research physicist, you do research, write papers. Why engage the public? Well, our machine was canceled in 1993. Our field was set back 20 years as a consequence. Right. Now the center of gravity is going to Europe. We lost the edge. You see, in the 1960s and 70s, during the Cold War, we would go to Congress and say one word, Russia.
Yep.
And Congress would open up their checkbook and say 2 words.
How much?
Those days are gone. Today, we physicists have to sing for our supper. We have to convince the taxpayers that they should fund physics.
Yeah.
And that's why we physicists now are trying to engage the public, because the Cold War is over. The Russians aren't building atom smashers. They're not competing with us in outer space. So we have to convince the public that, yes, your taxpayers' money is good because we can cure diseases, we can unravel the nature of who we are, explore the universe, and it's worth it. It's worth your taxpayers' money.
And I think that's one of the big questions. I mean, people have asked me why, when there's poverty, there's hunger, there are all these social issues that are so pressing around the world, why spend the billions of dollars on a machine to smash atoms?
Let me give you an example. When I was a child, polio was a big problem. Our president, Franklin Roosevelt, in the 30s had polio. And there was a debate in the scientific community whether we should build more iron lungs. Hundreds, thousands of children breathing in an iron lung.
Yeah.
Or we should devote a little bit of money to cure polio. Well, guess what happened? Jonas Salk cured polio with the vaccine, and all of a sudden, all these thousands of iron lungs were obsolete. Now, what's the lesson here? The lesson here is that we scientists don't do science just for the hell of it. Well, we do that too.
Yeah.
But what we do, the spin-offs of what we do, can cure diseases that affect tens of millions of people around the world. Okay? And some of it is by accident, and some of it is by design. But the point is that science is the engine of prosperity. Science is the engine of health. Okay? We ignore science at our own peril. We go back to the Dark Ages with all the superstition and diseases of the Dark Ages without science. We need science.
I have got some fun questions here that were sent to me by some of my friends on Twitter, and so I'm gonna pop a couple of these at you. Let's see. We have Justin Gill who wrote, with the discovery of the Bose-Einstein condensate, what possible exploits can be gained by humanity through its understanding, and what effects, if any, could be seen in everyday life?
Well, everybody knows the laser. We see the lasers everywhere. They're in our grocery checkout stand. They're in our CD player. The internet is made possible by laser beams. Laser beams are everywhere. But you see, lasers are based on light. Light that vibrates in unison, called coherence. Wouldn't it be better if we could do that with atoms? Have an atomic laser. Atoms vibrating in unison. If so, that would revolutionize computation. Quantum computers, quantum teleportation, all of that depends on atoms vibrating in unison, which is the most difficult thing to achieve in the laboratory. That's where Bose-Einstein condensates come in. Einstein showed that if you cool down a substance till it's really, really cold, all the atoms vibrate in unison and you have a superatom. A superatom. You can test all the bizarre features of the quantum theory for large objects because everything is vibrating in unison. But, says Einstein, impossible, because who could cool down something near absolute zero? Well, today we do that all the time. We cool down substances near absolute zero.
We're still not to absolute zero.
Yeah, we can't reach it. That's the third law of thermodynamics. But the Nobel Prize was given to scientists like at MIT that actually created Bose-Einstein condensates in the laboratory. What does that mean? Atomic lasers in the future. Okay? Some people even think that it may give us a shortcut to teleportation, a new way of just literally beam atoms across the room. if you can master the art of quantum coherence. For example, the CIA is interested in this because their computers will eventually run out of power. Silicon power cannot last forever. The CIA wants to crack codes. Some codes are very difficult to crack. If I have a quantum computer, I can crack the most difficult codes on the planet Earth.
Or create codes that are the most difficult to crack.
That's right. And remember that by 2020, the age of silicon will pass. Silicon Valley could become a rust belt after 2020. We could have a depression much bigger than the subprime mortgage crisis of today because silicon power cannot go on forever. Every Christmas, we assume that the previous Christmas our computers are twice as powerful. That cannot go on forever.
Right.
After a while, we have to go to quantum computers. Your Pentium computer has a chip that has a layer 20 atoms across. 20 atoms across, the smallest layer in your Pentium chip. By 2020, it'll be 5 atoms across. At that point, electrons don't know where they are because of the uncertainty principle and will leak out, and your computer will short circuit, and that will mean a depression in Silicon Valley. That is the end. So we physicists are desperately trying to negotiate that end with quantum computation, and Bose-Einstein condensates will be part of that solution.
That'll be great if we could solve that problem and continue on in our computing power.
Yeah, atomic lasers.
Definitely.
I mean, it boggles the mind to think what you can do with coherent radiation.
Yeah.
Star Trek, watch out.
So that goes into Salim Khan's question. He's interested in your take on what it would take to have a working quantum computer. So do you think it will be this further understanding of these Bose-Einstein condensates?
Well, a quantum computer goes beyond silicon.
Yeah.
So, for example, some of my friends who work on robots say that since silicon power doubles every 18 months, by 2050, we're all going to be in zoos. Our robot creations will throw peanuts at us and make us dance behind bars, just like we make bears dance behind bars today.
Right.
Wrong. There's a problem.
Okay.
By 2020, we will exhaust the power of silicon, as I mentioned, and it's not clear whether robots will be super powerful by 2050 because Moore's law is going to collapse.
Right.
Quantum computers, however, are not ready for prime time yet. The world's record for a quantum computation with a quantum computer was set by IBM. The calculation was 3 times 5 equals 15. That's the world's record, even today, for a quantum calculation. Why is it so important? That calculation was done on atoms, individual atoms, all vibrating in synchronization. The tiniest vibration, cosmic rays from outer space, could ruin the coherence, and your calculation is out the window.
Right.
But we think that quantum computers could be the way of the future if we can master the problem of decoherence. Impurities, a truck going by, vibrating, and all of a sudden your atoms don't vibrate in unison anymore.
Or just radiation. So if we're
Cosmic rays.
if we're using computers, these quantum computers in the future, say in outer space, where their rays were not as protected, by our electromagnetic field like the planet Earth is, but out in space they would be decohered very easily.
Right. So the good news to all of this is that maybe we won't have robots in 2050 that are smarter than us. But the bad news is we don't know what's going to replace silicon power. Maybe Silicon Valley will be replaced by a quantum valley if somebody masters the art of computing on atoms rather than computing on silicon.
All right. What would it take to make an honest attempt at lunar colonization? This is from Stephen Kellat.
Well, let's be real. To send a pound of anything into orbit, just orbit, costs $10,000 a pound. That is your weight in gold. Think of your weight in gold, solid gold, and then that's what it costs to put you in orbit. To go to the moon would cost perhaps $100,000 a pound.
Yeah.
To go to Mars would cost about $1 million a pound. Imagine your body weight in diamonds. That's what it would cost to put you on the planet Mars.
Right.
Now, by 2020, we're going to have a traffic jam on the moon. The Chinese have announced that they're going to go to the moon. In fact, they will probably beat the United States. NASA last year admitted that their time frame is behind the Chinese time frame.
And the Chinese are doing really well so far with with their orbiters and
Right.
getting up
And can
there.
you imagine all these nations putting flags in the moon
Yeah.
and bumping into each other? I mean,
Meep meep. Driving around in your little lunar rovers. Meep meep.
right. So you have to realize that it's very expensive. And look, when Columbus sailed the ocean blue, that's what most people say, he found riches and wealth in the New World. Yeah, because it didn't cost that much. Queen Isabella's bracelet, apparently, funded Columbus's voyage to the New World. And almost immediately they found the gold of Montezuma. Tobacco was a cash crop. The moon has no gold. The moon has no air. The moon has no water. Maybe helium-3 for our fusion machines. So I think space colonization, even though I'm all for it, is going to be longer term than we thought. Because, well, first of all, we have to leave the Earth. The Earth in 5 billion years will be destroyed. That's a law of physics. We will have one day, the last nice day on the Earth. The oceans will boil, the mountains will melt, and we're going to go back into the sun when the sun becomes a red giant.
When it starts expanding.
That's right. And on a scale of 50 million years, another dinosaur-killing comet or asteroid will hit the Earth. On a scale of 10,000 years, we're going to be under half a mile of ice. 10,000 years ago, we were under half a mile of ice. It's going to happen again in 10,000 years. So we have to leave the Earth at some point. As Carl Sagan once said, we have to be a two-planet species. An insurance policy, two-planet species. But he also said, what's the rush? It costs a lot of money to put men on Mars.
It does
and
cost a
people
lot
on
of
the
money.
moon. Right.
So it's a technological and a monetary.
I say let's do it with robots. Let's have a permanent robot presence on Mars and the moon. And then when prices go down, we can then start to put humans up there. For example, a space elevator could bring down the cost of space travel by a factor of 100.
Right. If there are also minerals on the moon that could be mined, maybe robots could go and mine for materials that could be used then, to build things and to take us elsewhere. But
it's easier to simply go to your backyard and mine things.
Yeah.
It's still cheaper.
It is. You bring up robots, and one of the themes of This Week in Science is This Week in World Robot Domination. So it's good to know that future might be further off than we're thinking.
And in fact, my point of view is that at some distant point in the future, when robots do become gradually more intelligent, instead of fearing them, we should either put a chip in their brain to shut them off if they get murderous, or we should merge with them. Because our descendants, hundreds of years from now, may have a choice. A, get older and older every year and die, or B, wake up in an genetically enhanced body of silicon and glass and live forever. So if you were faced with that choice, live a decrepit life, aging year after year, or be a Superman, young, handsome, virulent, and immortal, which would you choose?
Well, since you put the question so nicely, I want to be Superman. Well, Superwoman. Norbert K. asks, in what direction you see science heading, what should change, and what are your plans to change modern science?
Well, as I mentioned in my book Visions, a previous book, we are making the historic transition between the age of discovery to the age of mastery. We're no longer simply looking at the dance of genes. We're becoming choreographers of genes. We're no longer looking at the dance of atoms. We are becoming choreographers of atoms with nanotechnology and stuff like that. And we're no longer simply looking at building chips that can compute more and more. We're looking at what is intelligence and how do we break it down. So this means that in the future, we may have the power of a Greek god. Think of Greek mythology. In Greek mythology, the gods have the power to animate the inanimate, like in Pygmalion and My Fair Lady, or to recreate new life forms out of scratch almost. We will have that power. It's an awesome power.
Craig Venter already has that power. He's making his little microbes from scratch right now.
But pretty soon we're going to have a human body shop. Already we can grow skin, we can grow bones, cartilage, noses, ears, heart valves, blood vessels. The first bladder, human bladder, was grown from one's own cells about 6 months ago.
And I think last week I read an article about a three-dimensional printer that prints blood vessels.
That's right. I had a chance to see it. It's at Wake Forest University.
How
We actually did some filming there at that at that printer. Instead of inkjet coming out, it actually cells come out.
Yeah.
Next in line is the liver. Within 5 years, we hope to get the first liver either out of a printer or out of a mold of some sort. And think of all the drunks out there that are going to love the idea. No more cirrhosis of the liver, you know?
Yes!
Yeah, you can grow your own liver. The pancreas, maybe after that, maybe cure diabetes, who knows?
Which would be such a wonderful achievement for so many people.
And after that, perhaps even the spinal cord injuries, Alzheimer's, Parkinson's. With animals, we can do experiments that are unethical in humans, but we can inject brain cells into a damaged spinal cord of a mouse that can barely walk with its 2 front legs, but not the 2 hind legs. And after a few weeks, the mouse uses all 4 limbs to walk. It's an amazing video. This is impossible, medically impossible, regeneration of a spinal cord. And it's already been done. Yeah. It's been done already. So I can see that in the future we may have the option of recreating the human form. In mice, we've already found the smart gene, as they call it, for better memory. They're called smart mice. We already found the gene for the Mighty Mouse gene, or the Schwarzenegger gene if you're in California.
Strong mice.
And they have counterparts in humans. We too have the counterpart of the Smart Mouse gene and the Schwarzenegger gene. And so we may be in the process of self-creation, in which case laws may have to be passed, sermons are going to have to be given. How far are we going to redesign ourselves if we begin to understand the aging process? And we begin to extend the human lifespan. You know that for yeast cells, the world's record is we can multiply the lifespan of yeast cells by a factor of 10 times longer than the average yeast cell in the laboratory. We did that just about 6 months ago. Humans, well, who knows, but we may be able to tinker with the human lifespan because we're beginning to isolate the genes for aging. And in the future, all of us will have a CD-ROM with all our genes on it. We'll scan millions of these CD-ROMs, an owner's manual for our body. We'll scan the genes of old people, scan the genes of young people by the millions, and then subtract. Those are the genes for aging. We'll know exactly where aging is concentrated. And we already know that it's the mitochondria where most of the aging process takes place. In your car, where does your car age? Well, the engine. Where in the engine? The spark plugs, the place where carbon deposits gum up. That's the mitochondria of the cell. And we have cell repair mechanisms that we will accentuate, and we will extend the lifespan of a human being. That's coming.
I tend to agree with that. It's going to open up a whole new world. I mean, people in bioethics are already starting to consider it, the possibilities, which I think it's good to be ahead of the curve so that we don't end up, maybe having laws that are too antiquated before we get there.
Right. And this also, from a physics point of view, offers the possibility of enhancing a human being. For example, telepathy. Telepathy, of course, is the stuff of hokum and fortune tellers. And however, we think we can get limited forms of telepathy today, which I mentioned in my book, Physics of the Impossible. Today at Brown University, you take a stroke victim who is paralyzed. Paralyzed, cannot communicate with the outside world. Put a chip right on top of the brain, connect that chip to a laptop, and the person, by sheer thought, can manipulate the cursor of the screen, and that person can now play video games. That person can now answer emails, send emails, surf the web, and he is paralyzed. Think of this is going to revolutionize the way we deal with paralyzed people. And with normal people, we're going to take that object, which is about 2 inches tall on somebody's head, miniaturize it, stick it into people's brains if they want it, and you'll surf the web by thinking about it. No more mouse, no more stuff like that, booting up your computer. You'll just think about it and have the World Wide Web at your disposal.
Well, there are already there are cell phones that are being designed with the little headpieces so that they record and react to the premotor impulses, the thoughts about speaking, so that you can actually speak over a cell phone without having to use your voice.
And also with fMRI scans, this is causing a legal problem because lie detectors can be based on brain scans.
Right.
Telling a lie takes more energy than telling the truth. To tell a lie, you have to know the truth, know the cover-up, and the consequences of the cover-up, and the internal consistency of the cover-up.
Right.
Well, that's a lot of energy, and you can pick that up very easily on a brain scan. And this year is going to go to court. An insurance company denied somebody's claim, saying that you set your own house on fire.
Wow.
And the guy said, no, I'm going to sue, and I'm going to prove it by going to court and having my brain scanned in front of a judge.
Oh my gosh.
So it's going to be...
It's already happening.
In the future, we may have a dictionary of thoughts, different emotions, hate, love. We'll scan people's brains and have a dictionary. This brain pattern corresponds to love. This brain pattern corresponds with a dictionary of thought. Not quite telepathy, but we're getting there very fast.